So for induction, it would be more like, well, sorry, hold on. So it'd be more, okay, I've got this here, and let's say I bring this negatively charged rod near this sphere. What it's going to do is not that. That's not a very good picture. Let's pretend this was a bunch of positive charges. Okay? And so we bring the positive charge near it, but not touching. As you can see, they're not touching. And what it'll do is it'll attract negative charges over there, which will make this side close to it negatively charged and make this side over here positively charged. If we were then to connect this to ground, what would happen, all right, that's our ground symbol, is we could get a bunch of other negative charges to leave, because remember, negative charges are the charge carriers. They're the ones that move. Well, we have this positive side over here. It's going to attract negative charges over onto that, right? So it attracts a bunch of negative charges onto there. So we end up with these negative charges getting onto there and canceling out with those ones. We then remove this ground wire, right? That means all of these have now canceled out with something, okay? And let's pretend we take this away now. What do we have? We have an excess amount of negative charges there. So we have just induced a charge onto this without actually physically touching the two objects together. So that would have been an example of like how we could charge this by induction.
That makes sense.
Okay. And then the same thing is true if we were to have, we can do the opposite here. If we were to bring in something that was negatively charged, it would attract over the positive charges, which would repel the negative charge to that side, right? If we were to then connect it to ground, then all these negative charges would suddenly just start leaving. They would go as far away as they can. They'd go off, and therefore we would lose those negative charges. If we then disconnected the ground and then we removed this, we'd have a net positive charge on there. So by induction, if we're going to do something like through that means, we can actually charge it to the opposite of whatever we're bringing in. If I were to come along here and say I had this and it had a bunch of negative charges on it, and I were to actually physically touch them together, right? If they actually physically touched, assuming these were conductors, then what would happen is these would hop onto here and then they would spread out, right? So these excess charge would hop on here and they'd spread out like that. And then if I removed this, I'd have this thing negatively charged. That would be conduction as far as charging something goes.
That makes sense.
Okay. I know that's not exactly what that picture was made for, but hopefully that helps.
Yes, it does. Thank you.
Yep. What else would y'all like me to look at? And if you don't want to speak up while I'm recording, then you're welcome just to type it to me.
Can you explain like what capacitance is? I understand the picture and everything, but like what actually is it?
The actual capacitance itself. All right, so let's say you have, let's think of a balloon. And so you got a little balloon and there's no air in it, right? Now, let's pretend our balloon can stretch forever without breaking, right? If we hook up a hose and we put a hose into it like a nozzle and we pump in, say, I don't know, 2 PSI, we blow the balloon up to a larger size, correct?
Yeah.
And then if I change it to 4 PSI, it's going to go even bigger, right?
Mm-hmm.
And then, of course, if I go to like 20 PSI, it's going to get bigger. And the larger I make that pressure, the more air I can fit in there, right? And that's based on, like the stretchiness of the rubber, correct? If the rubber was really stretchy, then a little bit of pressure would be able to force more air in than a little bit of pressure could be able to force more in than if the rubber was really thick and really not very stretchy. I'd have to have a higher pressure to force more air in, correct?
Mm-hmm.
So when you think of capacitance, I think of it that same way. So we could essentially, in the balloon, we could figure out, all right, every time I put in, say, every time I increase it by 1 PSI, 1 pound per square inch, it increases by 2 centimeters in radius or something like that, right? Or 2 centimeters cubed, 2 more cubic centimeters of air can go into it. And so if I had this and I said, all right, now I put in, 10 PSI, what's the volume of the balloon? You should be able to figure it out from that, right? It would be 20 cubic centimeters would be the size of the balloon, correct?
Mm-hmm.
So capacitance is kind of telling you that same sort of thing, except instead of a balloon, we're talking about a capacitor. And what it's telling us is whenever we apply a certain voltage, so let's say we have our little battery over here, and yes, we haven't really learned the battery symbol yet, but there it is. One long line, one short line, positive side, negative side. And let's say this battery is 1 volt. Well, we know that when we put 1 volt on there, we end up getting, let's say, 1 coulomb of charge on each plate. Okay? And if I put 2 volts on there, I'm going to get 2 coulombs of charge. And so the greater of a voltage I put on there, the more charge I can put on there. And in fact, I could even write this out. I could say that for every coulomb of charge, I have to apply 1 volt across the capacitor. And so that's telling me my capacitance. And so if I told you now I applied 5 volts, you'd be able to tell me, oh, you're going to have 5 coulombs of charge on there because we have a capacitance of 1. Does that make sense?
Yeah, so if you raise the capacitance, like with a dielectric or something, are you increasing the amount of charge or the...
Yes.
So like for a smaller voltage, you'll be able to have more charge on the capacitor with...
Yeah, or for the same voltage, you get more charge.
Okay, that makes sense.
Yep, it increases capacitance. So if capacitance goes up and voltage stays the same, then charge has to go up.
Okay, that helped. Thank you.
Yeah, so that's the way I think of it. It's like a capacity of sorts, but it's flexible. So it's not necessarily like a bucket where you just keep putting more and more water in and it keeps filling up and eventually overflows. It's more like the balloon where the harder you try to put air into it or the harder you try to push water into it, the bigger it gets. And it's the same sort of thing. The harder we try, because remember, voltage is our potential to move a charge. So the bigger voltage we put on there, the more we can push that charge onto one plate, right? The more positive charges we can push onto this plate, the more positive charges get pushed off of this one and the more negative this one over here becomes. So that kind of a thing, like the more we can push, the more we can store on there.
What does the Q mean again in that formula?
Charge. Okay. And unless you're physically altering the capacitor, once you know the capacitance, you're set. So the only way to really physically alter them is to change the plate size, to change the separation between the plates, or to put something in the middle, the dielectric.
So there's an electric field in between the two plates, right?
Yes.
That's how it works. Okay.
Yes.
And the voltage that it sets is like the voltage for the electric field.
Well, I mean, that's kind of a philosophical thing. Does the voltage create the electric field or does the electric field create the voltage? There is a voltage, therefore there is an electric field. There is an electric field, so therefore there is a voltage.
Okay.
And yet, if you're between these two plates and they're very big compared to the separation, then you get a uniform electric field in between them. Just near the edges, you'd get some fraying, but in the middle of it, it's pretty uniform. Like in the middle part in there. All right, what else can we go over?
you go over Gauss's law and what we should know about that?
Yeah, was back in 19, right?
Yeah, it's like the last.
Yeah.
One of the last sections of 19.
So Gauss's law is all about the enclosed charge, wherever this is. Oh, there's a better picture for induction from earlier. I thought this picture was in there. I remember talking about it in class, but there it is. It was way down near the end. So first off, we have flux, the amount of field lines going through a surface. That's this flux right here. And then you find it by EA cosine of theta, where theta is the angle between the normal to the surface and the actual field itself. And we talked about that dealing with like a hula hoop in a river and stuff like that. Now, over here, what I talked about was that we could look at this divergence thing. And the idea is instead of counting up, instead of counting up all the faucets and stuff coming in, we can actually just count up the electric field spilling over that are spilling through the surface, which then would be the flux, because the flux is the amount of electric field through a surface. And so if that's the case, it means our flux is equal to charge enclosed over epsilon naught. All right. And so basically with this, what you have to do is fix a certain Gaussian surface that has the same symmetry. So like if you're looking outside a spherical shell of charges, then you'd want to pick a Gaussian surface that was spherical around it so that everywhere crossing that electric field, oops, that's a negatively charged sphere, hold on. Everywhere that electric field crosses, it's crossing it perpendicular to our little pretend Gaussian surface on the outside. And then all you have to do is look at the amount of flux going through your outer Gaussian surface, that's this side over here, and set it equal to the total charge enclosed. So however much charge is inside, enclosed in that Gaussian surface. And then you can solve it. If we go back, where is this one? There was one in here that had to do with finding the electric field between two charged plates, I believe. That was in here, wasn't it? Near the end, yeah, there, that one. And so instead of with a sphere, this is a Gaussian law with a, what is called just a cylinder, where if we look in here, we put one end of the cylinder, it's inside, this end right here is inside the actual metal there. So if it's inside the metal, there's no charge inside the metal because the charge always lies on the surface, and therefore the electric field inside a conductor, a charged conductor, is zero. So we have absolutely no field lines going through that end. For the walls of the cylinder, they are essentially, their normal is perpendicular to the electric field, and therefore it's the cosine of 90 degrees, which equals zero, which means we have no flux going through the walls. And therefore the only thing we have to worry about flux going through is this one end over here. And so the flux going through just this one end right here is all the flux we have. And it's going to simply equal the flux through the cylinder. Well, I wrote that all out. So here it is. So it's going to be the area of that cylinder. So that's 2 pi r. And then that has to equal however much charge we have enclosed. So here's the electric field times 2 pi r. That's our flux. And then on this side, we have our enclosed charge on the top. That's just the amount of charge that would be inside. If you look here, it'd be inside this little dotted part right there, because that's what's underneath, that's what's inside of our cylinder. And so I get that by doing the charge density, which they give me, times that area, because charge density is, it's charge per area. So I multiply by that area that's enclosed, and that gives me the total charge that's enclosed, I can then cancel out the 2 pi r's, and I end up with E equals rho over epsilon naught, which would be the strength of it. So we would look at this and say, all right, what's the electric field between the plates? It would be E equals whatever the charge density is divided by epsilon naught.
So charge density, when did that like come into play?
What
are you talking about?
Well, it's like what they said right here. They gave it to you. They said each plate has a charge per unit area of magnitude rho.
Okay, I was gonna say, I was like, I just don't know what rho is.
Yep. It's so charge per unit area. It's called the charge density.
Okay.
Anytime you have something that's like amount of something per some either linear length, area, or volume, they're a type of density. So like mass density, of course, is mass over volume. This is an areal charge density. It's a charge per unit area. There are some that are linear charge densities, which would be a charge per unit length. So like if you had a charged wire, like all just in a straight line like that, then you'd have a linear charge. And then you can have a charge density, which like volumetric wise, where you have a charge per unit volume. And there are energy densities as well, which I think, you probably should have heard of by now. You can have a certain amount of energy per unit volume or per unit area or stuff like that. Does that make sense? Maybe.
I'm still very much struggling to understand like what Gauss's law is saying at all. I don't know if anybody else is. I just like I don't really understand what it's meaning by.
All right. Let me undo everything I did here because I know some of the notes I wrote like were C green dotted circle. So let's go back over to, wait, where was it? 19 lecture. All right. Let's look at this page again. So if I have a bathtub and I have a faucet filling it up, right? Let's not even worry about there being any drains or anything in it. Okay, so just a bathtub filling up with a faucet, right? So it's plugged up. If I were to ever ask you how much water is coming out of that faucet, there's two things, or how much water is being pumped into the bathtub. You could come along here and count up how much water is coming out of the faucet, correct?
Yeah.
Yeah, that's what this is saying right here. That's saying count up all the faucets. That's what divergence is. It's telling you all the stuff that's diverging out from this place as the water enters the bathtub, okay? Or instead of doing that, because you might have a whole bunch of different faucets, maybe you have more than one faucets, maybe you have drains and stuff. You could also tell me exactly how much water was being pumped into the bathtub by looking at how much is overflowing from the edges, right? Because especially once this thing fills up, which we assume it's filled up, right? Every drop that comes out of a faucet is another drop that has to go over the edge, correct?
Mm-hmm.
And so if you look at that, what that does is it allows us, instead of, and you were in calculus with me, so I'm going to write this for you. So we'll have del dot E. So instead of summing up all of this in the whole volume, sum rho over the volume, right? Instead of summing up all of that over the volume, what I can do is instead sum up just the electric field that's going around and out the surface. So in other words, those two things equal each other. Do you agree with that?
It's been a minute. It's been a minute since calculus.
Conceptually, do you agree with the idea that I can either count up the amount that's coming in through the faucets, or I can count up the amount that's going out through the edges, and those should be the same?
Yes, that makes sense.
Okay. Over here, I'm summing up all of my charges. Epsilon naught, that's a constant. So that just comes out in front of the integral, right? But what is it if I sum up all of the charge per unit volume and I sum it up over the whole volume, what is that going to give me?
Wait, you said all of the charge over
If I
the
sum
whole
up
volume?
all the charges over the whole volume, and I know the charge per unit volume. So if I sum up that every little point I go to and I say, how much charge is at this point? And then I get that number. And I say, how much charge is at this point? And I get that number. And I go through and add up all the charges in the whole thing. What is that? Good.
I don't know.
That's the total charge.
Oh, well, that was like way easier than I was expecting.
Yeah. Don't overthink Gauss's law. It's pretty easy. Now, this gets kind of difficult. This is a difficult thing. But if we choose a situation where the electric field here is perpendicular to our surface area that we're looking at, this sum just becomes a very simple thing. It simply becomes E times A equals Q total over epsilon naught. Okay? And E times A is the flux. And in fact, we can even go ahead and make it fully the flux, because if it's not necessarily perpendicular, we do the cosine theta. But as far as Gauss's law is concerned, we're pretty much always going to choose it such that the cosine of theta is just 1. So we're pretty much always going to choose the electric field pointed outward through the surface. Otherwise, it makes this a lot more difficult, and we can't just easily get rid of that integral. Right? Add up all the electric fields over all the surface. That's just electric field times the surface area. That's all multiplication is. Add that up a whole bunch of times.
Okay.
All right. This is then just the Gauss's law we're using. The electric field times the area, and then the total charge enclosed over epsilon naught. Epsilon naught just a constant, so you can just carry that along.
Yeah, that was my next question. What is epsilon naught
E equals Q enclosed over the area, and then just 1 over epsilon naught. Is that making more sense or no?
I would never be able to apply that to any situation, but I'm understanding what you're saying.
Well, I mean, you can apply it here to a sphere. So let's say we had a sphere that had a charge, I don't know, let's say we had a sphere with a charge of 1 coulomb on it, right? So let's just add a page in here. So let's say we had a charged metal sphere, okay? Let's say it has a radius of r, and we'll say the sphere has a charge on it of 1 coulomb. We'll just keep it easy, okay?
Mm-hmm.
You to tell me 2 things. 1, what's the electric field a distance d from the center when d is greater than the radius and when d is less than the radius? All right? So now we have 1 coulomb of charge. So that means we have positive charges. This is a conductor. Charge conductor means all the charges are going to lie on the surface. So let's start out here. Let's make a Gaussian surface outside of here. We're going to draw just a sphere that's centered at the same location. I know that wasn't very good, but there we go. That's a little better. A sphere centered at the same location. And we're going to go out and put a radius of d on that sphere so that anywhere we are on that sphere, we are d away from the center of our charged sphere. Okay?
Mm-hmm.
Now, the electric field should be the same everywhere on that sphere, correct?
Yes.
Because the electric field is just going to go out like this. They're all the exact same distance away. The charges are all distributed evenly. So the electric field all over that surface is the same everywhere. So we just have to solve it for one of the places. So what Gauss's law tells us is we can do E times A is equal to the charge enclosed over epsilon naught. So that means our electric field is 1 over epsilon naught times the charge enclosed over the area. What is the area of our Gaussian surface, that green outer sphere? In other words, we have to spread this electric field out over that surface. What is the surface area of it?
The surface area of a sphere.
Yeah, don't remember it?
No.
4 pi r squared, which would be d squared in this case.
I almost said that, but I almost said cubed, and I knew that wasn't right. That was volume, so.
Okay, and so our electric field spreads out over the surface of a sphere, right? And it's the charge enclosed for it. Now, if we make d bigger, so say we had made our Gaussian surface way out here where d was bigger, then this d in the denominator would be bigger and we'd have a smaller electric field, correct?
Yes.
Because it'd be spread out on a larger and larger sphere as it got bigger and bigger. Okay? In fact, if we take a look at this, I can rearrange this a little bit. If I move this 4 pi, I have 1 over 4 pi epsilon naught, and then I have q over d squared. Doesn't that look, remember, doesn't it look an awful lot like just the Coulomb's law for a point charge?
Yeah.
It's the exact same law. So what we're saying here is outside of that charged sphere, we can actually treat it as though it was the same amount of charge, all just located right at the center.
Mm-hmm.
Like
so
it was a point charge.
It's basically saying like it doesn't really matter how big the circle is. You can figure it out like for however.
How big the sphere is. As long as you're outside it, yeah, it's just going to be that law for that spherical symmetry.
Okay, and then what are the two different situations for D is greater than R and D is less than R?
Now D is less than R. Let's do that one. So D is less than R. That means we have a little surface inside of here. We'll call that the little d right there, okay? If D is less than 0, we have E times A equals Q enclosed over epsilon naught, okay? So if you look at this picture, look inside the orange sphere there. How much charge is enclosed?
None.
None. So I come over here, this Q enclosed, that's a 0. This is E times A equals 0.
Oh.
Which means we know the area of our sphere is not 0. That means our electric field inside there is 0. And it turns out that is absolutely true.
Okay, that makes more sense. Okay.
All right.
Thank you.
And then you just have to worry about what kind of a symmetry you do. If you're doing a plane surface, like a plane, that's like the one that I just was talking about here, and you use like the little Gaussian cylinder like that. If you're doing a line, if you're doing like like here's a line and it has a certain charge density to it, you know, like a linear charge density rho. So charge per length. You would do another cylinder like this around it. And the electric field coming off of this thing is going to point out radially, kind of like this in all directions. It's going to point out like that. And then what you'll say is we can ignore the ends because the ends are not going to have any of the flux going through them. And so here, E times A equals Q enclosed over epsilon naught. The area is just the area of the cylinder, right? The wall of the cylinder. So whatever the radius of the cylinder is, let's call it R, that is going to be 2 pi RH. So E is going to equal 1 over epsilon naught, our charge enclosed over 2 pi R times the height, whatever H we're looking at there, right? But then the charge enclosed has to be right here, Q equals rho times L, right? Our density times the length. Well, the length we're looking at here, in this case, is H, whatever the height of our cylinder is. Do you agree with that?
Wait, so H
is
only measuring the length of the cylinder?
That's the length. The length of the wire that's enclosed in the cylinder is the length of the cylinder.
Okay.
Right?
Yeah.
So therefore, our L becomes H, rho H, which means when we put this in, it's 1 over epsilon naught rho h over 2 pi r h, and our h's will cancel. And we can say the electric field around a wire, a charged wire, infinitely long one is, or really long one, is rho over 2 pi r, which is interesting because I think that's the first time that y'all will have been seeing something that dropped off as 1 over r instead of 1 over r squared.
So in that other math problem, why did you put the cylinder going through the plate?
Well, if I had put the cylinder, if I had drawn the cylinder this way, I mean, I'm not sure how that would have worked. I don't have the symmetry to take care of. Now my electric field is coming out this way, which means it's not everywhere perpendicular to the surface, right? I'm going to have no flux through the ends of this again, right? But what about these little parts over here? You know what I mean? Like that side, if we took and blew that up, we'd say, all right, here's this little part of the cylinder, right? The electric field is coming out this way through it, and it's absolutely not perpendicular, right? Because, it's curvy. Like if we looked from above, the electric field would be coming through like this. There it's perpendicular, but over here, it's not perpendicular in there. With an above view, you see what I'm saying?
Yeah, but how is it perpendicular the way you have it also?
Well, the way I have it up here is it's either everywhere the electric field comes out, it's perpendicular everywhere all over that surface, right? It's coming out straight through the end of it.
So you're measuring it just on the end versus like going through the side.
Well, it doesn't go through the sides. It runs.
Well, I mean, like in your other, like your line example, it was going through the side.
Yes.
Okay.
You mean?
No, for the like.
Go back to the other page.
Like you were having it so that the field was pointing out.
Yes.
Okay.
And the field from that is going to point out radially from our line. Let me get rid of all this. Hold on. Okay. So if we go back to that one, the field coming from here, like if we were looking at the wire, say the wire was coming out at us like this, right? Here's our charge of line. The field is going to be pointing out like radially like this, like spokes on a tire.
Mm-hmm.
So when I put a cylinder around it, right? Let's test out my 3D drawing here. When I put a cylinder around it, those coming out are perpendicular to the walls of the cylinder everywhere.
Okay.
Right? Kind of like if this was the end of our wire, here's our cylinder around it, and the field's coming out this way. We're looking from the end of the wire, like the wire's coming out towards you. This is the wire. This is our Gaussian sphere outside of it, or Gaussian cylinder, sorry.
Yeah, I think the example just confused me because like the electric field is only going in one direction. So like it's just going straight across.
Which example?
The one on the one you did like in the math problems.
That one?
Yeah.
Yeah, that one's just a uniform electric field between two plates. Okay. What else can I go over? Any other problems or any other concepts or ideas or anything I can talk about here for y'all? Clear up?
Are we gonna have to like know the volume formulas if you give us a cylinder and?
Hey, you got your card. You write whatever you want on it, right?
Yeah, but how am I supposed to know what shape you're gonna give me?
It's probably not going to be anything worse than a circle, a sphere, a cylinder, or something like that. I mean, you're not going to get something that's not a sphere, a cylinder, or pretty much that's it. I don't know what else we could do, really.
Okay.
We can't do the more complicated ones. We don't know calculus. So, yeah, usually you just need to know cylinders and spheres and stuff like that. I guess if you see it in the homework, write it down. In case I'm forgetting something right now.
If you put one of those donut shaped things over the bane of my existence in calculus, I'm going to be angry. Torus or something.
You mean, wait, where we did the integral and found the volume of it?
Yes, and the surface area. I wanted to.
Oh yeah, that wasn't bad.
Oh, come on.
All right, what else can we do?
This is a very broad question.
Okay.
I feel like in the homework when there was equations that a certain like variable is supposed to be negative, and then in the in the homeworks it's like they forgot about the variable in problem solving. Like in question 41, in the homework of chapter 20, it's asking for the work done, and it's using like the change in potential energy. So the change in potential energy equals negative work, but the answer wasn't negative. So I'm just confused, like.
Wait, they asked for the work done or the potential energy?
So they were asking for the work done, and they gave
Did they happen to say magnitude of the work done?
No, it just said calculate the work done by an 8-volt battery as it charges a capacitor, an 8.6 force capacitor in the flash unit of a camera.
So you should end up, well, for that one, I would go ahead and say just do, for that one, I would just say, okay, here, all I'm going to do is, I know I'm putting energy into the system, so the battery is giving energy to the capacitor. That means that battery is doing positive work. So for that one right there, you should have a positive work at the end. And so typically for stuff like that, I think what they do is expect you to think of it that way, and then you ignore signs, especially for one like that where it's a capacitor, because at the end, should you use a positive charge there or a negative charge? Because remember, one plate is positive and one plate is negative. So for that one, it's like a little bit of do the math, but also you got to know this concept, because you need to know that the charge capacitor is both positive and negative depending on which plate you're looking at. And then you have to just kind of know, well, it's definitely giving energy to the capacitor, so it has to be doing positive work.
Okay.
So, right, anytime you're giving energy away, anytime something's giving energy to something else, it's doing positive work on that thing. Does that make sense or not really?
Yeah, it does. I just felt like I kept having I guess I was just I'm confused still about the why you put the negative in that equation, so that just throws me off.
It is. You're talking about with the V equals negative ED.
Yeah, like in the electric field using negative V, just all the just the random negatives just throw me off.
I know it is. There's nothing. You know what? Like I said that in class, there are times when I have to really just sit there and stop and think it through, and make sure I'm doing it the right way, and make sure that at the end I get the sign that I know I'm supposed to. So quite often, a lot of times, what is done here, because we have so many positive and negatives, is you typically tend to want to say, this is what it should be. You know, this is what it should turn out to be. I know that these two should be opposites. I don't really necessarily have to know which one is positive, which one is negative. I just know they're opposites, so they're going to subtract from each other. And then I know in the end, I'm supposed to have something that is negative. So therefore, I make it negative. It's just something that's done a whole lot in this area of field.
She is right, though. The homework randomly will drop out negative signs and give no explanation.
Yeah, I'm sorry about that, but it's probably just they're expecting you to realize something like the one I did over here. This one, actually, where I tried really hard to make sure I got the signs correct for each one of these. But like if you look at, again, I bring the first one, it doesn't take any work. The second one, when I bring it in, so when I'm bringing in this charge near this charge, right? Pretend this one over here isn't there, okay? When I bring that in, this negative charge has a negative field to it, correct? So when I do that, that means that around that charge, the electric field like the electric field from this negative Q is pointed toward it, correct?
Yeah.
So when I put the 3Q charge right there, I just brought it in from, see, I don't have enough room here. Man, there's just not enough room on these. Let me add one in. Okay. Let me start that. Let me start that argument over again. Let me add that in and get rid of these things. Okay. So okay. So if we have a negative charge right here, and then I bring in, say this is infinity way over here, I bring a positive charge over toward it, right? I bring that positive charge to there from infinity, okay? So this was my positive charge over here out of infinity. I bring it over there. I know that I'm going in the direction that the electric field is pointed, right? And so there's two things that tells me. One, if I'm moving in the same direction that the electric field is pointed, I am decreasing voltage. So that means that from out here all the way to here, I have a negative voltage drop. But I also know that if I am taking a positive charge and making it do what it wants to do, it's losing potential energy, correct?
Yeah.
So that's how you go through and you think about these things. And then you have to ask yourself, am I looking at the energy change of the field or the energy change of the particle? Because one of them is going to be positive and one's going to be negative. So like if we looked right here, this would have lost potential energy, right? And gained kinetic energy, but the field itself is going to do the opposite. So if it's the work done by the field, we have a positive amount of work done.
I have a question.
Yes.
What if that negative was going to the positive? Would it be the same like behavior as the positive going to the negative?
Yes, we would have the same amount of work there because let's change it around. All right, our negatives from really far away, right? The negatives coming from way over here. The positive charge is putting out electric fields that way, correct?
Okay.
Away
yes.
from it. So now we're moving the electron or the negative charge against the electric field, which is the direction it wants to go, which means it's gaining potential energy, which means the field is doing negative work on it.
It's also,
How would it be
also
gaining?
going up in voltage though, right?
It is, yeah. Well, see, that's the thing you have to be careful about. Let's change that, what you just said there. The negative charge does not go up in voltage. It moves from a point of low voltage to a point of high.
Oh, yeah. But it's going to higher voltage because of that negative ED thing, right?
Yes.
Okay.
Well, why would it be going from a low place of voltage to a high place of voltage if a negative charge is attracted to a positive charge?
Because voltage doesn't have anything to do with the actual charges that's in the electric field.
So the attraction of charges and the behavior of them are two different concepts in this.
No, I don't think. I'm thinking about what you said here, and I'm trying to think of the best way to explain it without causing the big giant. Casey?
Yeah.
Did you ever actually get this understood? Was there something in particular I said to you that day when you and a few others stayed late and chatted with me?
Yes, I do believe I understand this. And I just have to think of voltage as like a completely separate, like not that it's a completely separate thing, but I just have to think of it like the density really helped me understand. Like relating all the variables to like a density situation really helped me understand. Because like also I just have to come to grips with like the fact that it's just like higher in one spot and lower in one spot because of convention. Like, you know what I mean?
It could be reversed. We could have very easily not put a negative sign in there, in which case negative charges would be going against the electric field and going down in voltage.
Yeah, that's exactly like as soon as I learned that literally it could be different if you just like switched the negative sign, like where they wanted to put it, then I kind of started to understand it.
So let's say we have this electric field right here, okay? We have no idea what's creating this electric field. okay?
Okay.
If we have point A over here, or line A here, that's an equipotential, and then equipotential B over here. So it's the same potential everywhere on that dotted line for A and everywhere on that dotted line for B. I know this because I'm crossing every electric field line at a right angle. So therefore that's an equipotential.
Okay.
If I take a neutron, which has no charge, correct?
Yes.
And I move that neutron from point A to point B, I have now moved that neutron to a point, from a point of high voltage to a point of low voltage, or a high potential to a low potential.
Why?
Because that's what we define in the field. The voltage is a property of the field, not a property of the charges that are in it.
It's like it's rolling down a hill, Joel.
That doesn't help me. I don't understand that.
So like
Except
A, you're on
it's
top
like
of the
having a
hill.
hill, but something would roll down it if we had something to roll down it, but it's still a hill even if we don't have something to roll down it. The hill,
So what
the
electrical
slant
field?
of a hill is a property of the hill, not a property of the ball that's rolling down it.
Okay. And so then what makes an electrical field? Because I thought once you put a charge,
Charges
Or
make
like-
electric fields.
right. But you just said, let's just say we have an electrical field. We don't know what made the electrical
Well,
field.
we're just ignoring it for the moment. It's the same thing. I can
Okay.
have a mountain. I can have a mountain right here, right? But
Mhm.
what that mountain's made out of, if I start rolling a rock down the mountain, right? The mountain itself is made out of rock, but I don't have to worry about that, do I? I just have to
No.
know the elevations of it and how steep it is, correct?
Yes, that makes sense.
So yes, electric fields are made by charges, and then they also are affected by, they create electric fields they're, so if I have a charge here that makes an electric field, its own electric field, it's not affected by its own electric field. Its electric field does affect other charges that are around it. So say this is charge 1 and this is charge 2. Charge 1 creates an electric field that affects charge 2. Charge 2 creates an electric field that affects charge 1.
Okay.
And it's kind of like this. If I have if I have a bunch of rocks here that are piled up to make a hill, right? Rocks, atoms, and molecules make the hill, and then rocks, atoms, and molecules or whatever make the thing that's rolling down it too.
Right. So if you had to force the ball
sorry.
to roll down, if you had to force the ball to roll down the hill, that would be an increase in potential energy and an increase in voltage, correct?
If I had to force it to roll down the hill, then I guess that would be more like the negative charge moving against the electric field.
Right. Would that be an increase?
With it.
Would that be an increase in potential energy and voltage?
So if this is some kind of magic ball that likes to roll uphill and is always looking to get to the tops of hills and hates being at the bottom, then forcing it to go down the hill would be an increase in its potential energy.
Would it also be an increase in voltage?
Decrease in its elevation.
What would happen to the voltage?
The voltage is like the elevation. So if I had a ball that always rolled uphill, never rolled downhill, right? If I force it to go down a hill, I'm increasing its potential because by the time, if I have it at the top of the hill, it's just going to want to stay there.
Right.
Move it to the bottom of the hill, it's going to want to go back up and it's going to gain kinetic energy going back up, right?
Yes.
But if I have it at the top of the hill and I move it to the bottom, that's an increase in potential energy for this magical uphill rolling ball, and it's a decrease in its elevation.
So it's a decrease in voltage?
So if I have a negative charge right here, which way would the negative charge want to move?
Against the electrical field.
So the negative charge wants to go to the left. If I force it to go to the right, I'm increasing its potential energy, correct?
Yes.
What happens to the voltage from where it started to where it ended?
Wouldn't it also increase?
So this was high V, this is low V. Remember,
So it
like the ball that rolls up the hill. It's like going up the hill right there, which means it's decreasing in voltage every time, just like the ball that go. If we let the ball roll down the hill, no matter what, if it's an uphill rolling ball or a downhill rolling ball, if we move it down the hill, it's a decrease in elevation, right?
Right.
So no matter what we do with any charge, a neutral charge, a negative charge, a positive charge, if we move it in the direction of the electric field, it's moving toward a decrease in voltage. So delta V is less than 0. Delta V less than 0. Delta V less than 0. Potential energy here for this one, change in potential energy, 0, because it has no charge.
Right.
For the neutron. For the negative charge, the change in potential energy is greater than 0. It's increasing in potential energy because it wants to go the other way.
Right.
Positive charge, that's the way it wants to go. So its potential energy change is less than 0. It's decreasing.
So like
Okay.
relating to the concept of voltage, like the ability to move a charge, does that mean like down the electric field, there's like less ability?
Say that again?
Well, because you know how you explain voltage as like the ability to move a charge?
Yes. Yeah.
So as at like a point of lower voltage, is that like there's less ability to move the charges at that point? I don't know if this matters or not.
Again, you don't, it depends. No, you're not asking that quite right. So how can I put this? You don't care. So, oh man, I don't want to say this without confusing y'all more. Yeah, I don't like the way you just stated that. Let's say we call this V equals 0 right there. And this is just some other V. V equals, I don't care, 10 volts, let's say, right? And let's just pretend that's it. Everywhere else, you know, everything to the right of here, the electric field dies, it stops right there. There's no electric field over here, okay? If I put a positive charge right here, it's not gonna go anywhere. Do we agree?
Yeah.
If I put a negative charge right here, what's it gonna do?
It's gonna go the other way.
Against.
Right. So just saying the voltage is 0 or is the voltage is lower means it has less potential to move a charge. What depends which charge you're talking about.
So it is affected by which charge you're talking about.
Of course, for how it will then be affected by the voltage. Again, the voltage is a property of the field that can tell you how that field will affect a charge. And different charges are affected differently by voltage.
I think I'm just kind of confused because like the voltage changes through the electric field, but then like in a capacitor, when you have like a battery setting it at like 20 volts, does that mean it's 20 volts across the whole electric field, or does it go down?
Pretty much. There is some slight decreasing that occurs in the wires, but it's very negligible. Those wires are extremely good. Because they're so good conductors of charges, they're extremely good waveguides for the electric fields. And so therefore there's really no like decreases that's going on in the voltage in the lines. Technically there is a little bit, but it's very, very little.
So in like problems that are figuring out the electric field for that, there isn't like a change in voltage.
There is once you cross the capacitor. Think of it like this way. Like let's say we have the battery here, right? And then the battery comes around and then we'll put the capacitor here. That's a parallel plate capacitor. And then we come over here. So if we send something out, right? If we send a positive charge out, so this part right here is going to be the high voltage side. Let me zoom in here. This is going to be the high voltage side. So if this is 12 volts, it means there's a difference between the positive and the negative terminal, that this side is like 12 volts and this side is 0 volts. Okay?
Mm-hmm.
So then we take, and a little positive charge moves along here, and it comes along here. Now, technically through the wires, there is a little bit of drop in potential, but it's not really till it gets to here across the device that we really get the drop. Okay? And so as soon as we get here, this thing is going to, you know, let's pretend this isn't even a capacitor. Let's just say it's like something like a light bulb or something, right? It's just some kind of something. This thing is going to suddenly drop down to 0 volts and then come on back around to this side to cancel out with a negative charge over here. Okay? So it dropped down and lost that voltage. The way I think about this is I think about it like one of those rides you get on, like if you, what is that ride at Disney where you go up in the mountain, Splash Mountain, right?
Okay.
You have a bunch of conveyor belts and pumps and stuff like that that pump you and the water from down low. They pump you up high, right? And then you go down the waterfall. And if you want, then the cart goes around again and it gets pumped back up to the top. So you have some sort of pump or some sort of lift thing here that lifts your boat and the water up to the top, and then you fall back down. It's the same thing here. This thing pumps charges up with energy, sends them around where they then go down. They go down the hill. Like this is the slide, whatever our circuitry is the slide, drops down and then comes back over here before this has to give it energy and pump it back up again.
So if I was like figuring out a problem of the electric field of a capacitor that had like a battery of 12 volts going onto it.
Yeah.
In between the two plates, could I assume that the left side was 12 volts and the right side was 0 volts?
Sure. Or you could do the left side. Well,
like depending on which side.
The positive side.
Yeah.
So let's say we're looking at something like that. Here's what we can do. They tell you have a capacitor, parallel plate capacitor, positive one, negative one. You could call this 12 volts, 0 volts. You could call this 24 volts, 12 volts. You could call this 0 volts, negative 12 volts, right?
Yeah.
This could be 14 volts and 2 volts. All that matters is the change.
Mm-hmm.
Like if I have a hill, right? I could call this 0 feet and this 10 feet. I could call this 10 feet and this 20 feet. I could call this, you know, negative 10 feet and this 0 feet. All that matters is the elevation change is 10 feet.
Mm-hmm. And it's going from higher to lower. Like,
well, I didn't say anything about who was going high to low.
Well, I mean, but like if you,
I could be pushing a ball up the hill that's going from low to high, or I could be letting a ball roll down the hill that's going from high to low.
Yeah, but reading left to right, like just the field without any charge in it. But like if the battery like set it at 12 though, it would be like the 12-0 situation, or would it matter?
If the battery is 12 volt, it doesn't really matter. 12
so it's just a change to 12. Okay.
We just need to know it's change up. So you pick the one that's easiest. Usually that's easiest.
And it goes higher on positive to lower on the negative.
Yes, that's the way the electric field is pointed.
Yes.
Remember,
okay.
Voltage decreases if you're going in the direction of the electric field.
Yes, that's what I meant.
That's out of positive in the negative, therefore that's a drop in voltage.
Yes.
Doesn't potential energy also increase when you're going against the electrical field?
Potential energy increases for a positive charge going against electric field. It decreases for a negative charge.
Okay.
Like up here, where our negative charge was going with the electric field and the potential energy increased, our positive charge was going with the electric field and the potential energy decreased.
Okay, now what about voltage?
Both of them, voltage drops. Because
see, I don't understand
based on
that.
the field, not the charge. You're only looking at location. Voltage is location based, not the charge that may or may not be moving based. Just like up here, with the neutral charge, we still are moving from a place of higher voltage to lower voltage. Still a voltage drop, even though we have no change in potential energy.
So the voltage is set by the electrical field.
The voltage is set by the electric field, just like the steepness of a hill is set by the rocks that make up the hill, not the rock rolling down it.
Yeah, Jewel, I finally had to think like the voltage is high on one side and low on one side. Like that's just the way it is.
Okay, that's all I need to know. Now I get
Like,
it. As long as it's good.
like a hill. I know I keep
So
saying,
how do we
I
determine,
just don't know a better, I don't know a better analogy to give than that one.
I just think because of the formula, my mind gets all like, confused
Yep.
because of relationships, and I use formulas to understand concepts. And so with this, I can use it, but I have to think about the concepts correctly in order to use it, which is what I'm struggling.
Which formula is messing you up?
The delta V equals delta U divided by charge, Q, divided by Q. Yeah.
Oh, that's that same one, huh? This one, I think what got Casey finally fixed was thinking of it like a density. We're not actually having that charge in there. It's the amount of voltage tells us the amount of potential energy we would have for a charge if that charge was there. Kind of like density tells us the amount of mass we would have for a certain volume of that material, right? So
yeah.
if I had this and I said, all right, I'm going to give you a cubic meter of steel, and you knew the density of steel, you could immediately tell me, oh, you're going to have this much mass. But if I said, now I'm going to give you 10 cubic meters of steel, you'd change this around and say, oh, I'm going to have a different amount of mass, correct?
Yes.
Well, it's the same sort of thing here. I'm telling you there is a potential associated with the field. And then if I tell you this charge is going in the field, you'd say, oh, that charge, it'll have this potential energy. And then if I change it and say, oh no, now instead of a 1 coulomb charge, it's a negative 10 coulomb charge. Now you say, oh no, wait, now here's the new potential energy. Just like over here, you'd say M equals rho V. Over here, you can use it and just say that delta U, our potential energy, is QV. Of course, that's voltage and that's volume. Don't confuse them.
So would you say that voltage, in a sense, is constant?
Voltage drops between two locations where the field does not change. Yes, it's going to be a constant. If it's between the two same locations and you're not changing the field, then the voltage drop will be the same.
Okay.
Or the potential difference will be the same. Voltage, potential, voltage, electric potential, potential difference, they're all saying the same thing. Some people make distinctions between them. I find distinguishing them is confusing because technically it's always potential difference. It's always the difference. So taking the word difference off is kind of nonsense.
And how would we know, like, so would a problem say the voltage is from going from high to low, or?
You usually have to figure that out yourself. They might just tell you there's a voltage drop across this, or there's a voltage drop between these plates. And then if you look at the positive plate and the negative plate, you should know which direction the voltage drop is occurring. It's dropping as you move away from positive and towards negative. Or as you move in the electric field, voltage is dropping. It can be just you moving around an electric field, you being totally neutral. The voltage will change as you move around. It's just the voltage isn't going to affect you.
That makes sense. I had to think about it. That makes sense.
Yeah. Kind of like in old bad video games where if you start running uphill, it doesn't change your speed at all. You ever play old games where something like that would happen? Or even if you ran uphill and it didn't change your horizontal speed. So like you went uphill and you actually would speed up such that you covered the same distance across, sideways on the screen. I guess that would be like being neutral in a voltage. is like the old bad video games. I don't know if that's a good analogy or not, but you're not affected by the landscape.
Just true.
If you're neutral.
Makes sense. It really does. It makes sense now.
Okay.
Thank you.
Anything else?
You said this exam was more conceptual than math, right?
Yeah, I think I took just conceptual or just math problems off of it. And it really kind of also depends on, you know, how you approach them. There's a lot of conceptual stuff that you can answer mathematically, and a lot of mathematical stuff you can answer conceptually, or at least skip a lot in both. So I kind of always tend to look at every conceptual problem and every math problem as a hybrid of both. And then it kind of is up to you whether or not you spend more time doing it conceptually or more time doing it mathematically. All right, anything else? No? All right.
I think we're